Hi, and welcome to the new section of the course, Processing the Colors of an Image. In this section, we will be comparing colors using the StrtegyDesignPattern. Then we will be segmenting an image with the grab-cut algorithm. After that, we will convert color representations, and finally we will be representing colors with hue, saturation, and brightness. So let's begin with the first video titled, Comparing Colors Using the StrtegyDesignPattern. In this video, we will write a simple program that will run our proposed color detection algorithm, then look at computing the distance between two color vectors, and finally explore the floodFill function. Let's say we want to build a simple algorithm that will identify all the pixels in an image that have a given color. For this, the algorithm has to accept an image and a color as input, and will return a binary image showing the pixels that have the specified color. The tolerance with which we want to accept a color will be another parameter to be specified before running the algorithm. In order to accomplish this objective, this video will use the StrtegyDesignPattern. This object-oriented design pattern constitutes an excellent way of encapsulating an algorithm in a class. It becomes then easier to replace a given algorithm with another one, or to change several algorithms together in order to build a more complex process. In addition, this pattern facilitates the deployment of an algorithm by hiding as much of its complexity as possible behind an intuitive programming interface. Once an algorithm has been encapsulated in a class using the StrtegyDesignPattern, it can be deployed by creating an instance of this class. Typically, the instance will be created when the program is initialized. At the time of construction, the class instance will initialize the different parameters of the algorithm with their default values, so that it will immediately be ready to be used. The algorithm's parameter values can also be read and set using appropriate methods. In the case of an application with a GUI, these parameters can be displayed and modified using different widgets, text fields, sliders, and so on, so that a user can easily play with them. We will show you the structure of a strategy class in the later part of the video. Let's start with an example of how it can be deployed and used. Let's see a simple main function that will run our proposed color detection algorithm. Here we have created an image processor object, and these two lines are used to read the input image. To set the output parameters, we have defined this line, and then the processing and displaying of the image will be done here. Running this program to detect a blue sky in the colored version of the castle image produces the output that you can see on the screen. Here, a white pixel indicates a positive detection of the sought color, and black indicates negative. Obviously, the algorithm we encapsulated in this class is relatively simple. The StrtegyDesignPattern becomes really powerful when the algorithm to be implemented is more complex, has many steps, and includes several parameters. The core process of this algorithm is easy to build. It is a simple scanning loop that goes over each pixel, comparing its color with the target color. So this can be written as follows. Firstly, this block of code gets the iterator and the loop for each of the pixels to compute the distance from the target color. Here the CVMat variable image refers to the input image, while result refers to the binary output image. Therefore, the first step consists of setting up the required iterators. The scanning loop then becomes easy to implement. Note that the input image iterators are declared constant as the values of their elements are not modified. The distance between the current pixel color and the target color is evaluated for pixel in order to check whether it is within the tolerance parameter defined by maxDist. If that is the case, the value 255 for white is then assigned to the output image. If not, 0 for black is assigned. To compute the distance to the target color, the getDistance to target color method is used. There are different ways to compute this distance. One could, for example, calculate the Euclidean distance between the three vectors that contain the RGB color values. To keep this computation simple, we sum the absolute differences of the RGB values. This is also known as the city block distance. Note that in modern architecture, a floating point Euclidean distance can be faster to compute than a simple city block distance. In addition, you can also use squared Euclidean distances to avoid the costly square root. This is also something to take into consideration in your design. Also, for more flexibility, we write the getDistance to target color method in terms of a getColorDistance method, like this highlighted part. Note how we use CVVector3D to hold the three unsigned chars that represent the RGB values of a color. The target variable obviously refers to the specified target color, and as we will see, it is defined as a member variable in the class algorithm that we will define. Now, let's complete the definition of the processing method. Users will provide an input image, and the result will be returned once the image scanning is completed, and that is done by adding these lines of code. Here, this line relocates binary map, if necessary of same size of input map, but as one channel. So each time this method is called, it is important to check if the output image that contains the resulting binary map needs to be reallocated to fit the size of the input image. This is why we use the create method of CVMat. Remember that this method will only proceed to relocation if the specified size and/or depth do not correspond to the current image structure. Now that we have the core processing method defined, let's see what additional methods should be added in order to deploy this algorithm. We have previously determined what input and output data our algorithms require. Therefore, we define the class attributes that will hold this data, such as class color detector private. And this will accept the minimum distance, and the target color is defined here. This will hold the image containing resulting binary map. So in order to create an instance of the class that encapsulates our algorithm, which we have named color detector, we need to define a constructor. Remember that one of the objectives of the strategy design pattern is to make algorithm deployment as easy as possible. The simplest constructor that can be defined is an empty one. It will create an instance of the class algorithm in a valid state. We then want the constructor to initialize all the input parameters to their default values. In our case, we decided that a distance of 100 is generally an acceptable tolerance parameter. We also set the default target color. We choose black for no particular reason. The idea is to make sure we always start with predictable and valid input values that can be done using this line of code. Another option would have been not to create an empty constructor and rather force the user to input a target color and a color distance in a more elaborated constructor, which can be using this highlighted code. At this point, a user who creates an instance of our class algorithm can immediately call the process method with a valid image and obtain a valid output. This is another objective of the strategy pattern, that is, to make sure that the algorithm always runs with valid parameters. Obviously, the users of this class will want to use their own settings. This is done by providing the user with the appropriate getters and setters. Let's start with the color tolerance parameter. So here, we have getters and setter method. This block of code will set color distance threshold, and threshold must be positive. Otherwise, the distance threshold is set to 0. Note how we first check the validity of the input. Again, this is to make sure that our algorithm will never be run in an invalid state. The target color can be set in a similar manner as we have done here. This time, it is interesting to note that we have provided the user with two definitions of the setTargetColor method. In the first version of the definition, the three color components are specified as 3 arguments, while in the second version, CvVector3b is used to hold the color values. Again, the objective is to facilitate the use of our class algorithm. The users can simply select the setter that best fits their needs. The example algorithm used in this video consisted of identifying the pixel of an image that has a color sufficiently close to a specified target color. This computation could have been done otherwise. Interestingly, an OpenCV function performs a similar task in order to extract a connected component of a given color. Also, the implementation of a strategy design pattern could be complemented using function objects. Finally, OpenCV has defined a base class, CV algorithm, that implements the strategy design pattern concepts. So next is computing the distance between 2 color vectors. To compute the distance between 2 color vectors, we use these simple formulae. However, OpenCV includes a function to compute the Euclidean norm of a vector. Consequently, we could have computed our distance as this block of code. A very similar result would then be obtained using the definition of the getDistance method. Here, we use CvVector3i because the result of the subtraction is an integer value. Next, we will see using OpenCV functions. In this video, we use the loop with iterators in order to perform our computation. Alternatively, we could have achieved the same result by calling a sequence of OpenCV functions. The color detection method will then be written as follows. This method used the absdiff function. which computes the absolute difference between the pixels of an image and, in this case, a scalar value. Instead of a scalar value, another image can be provided as the second argument to this function. In the latter case, a pixel-by-pixel difference will be applied. Consequently, the two images must be of the same size. The individual channels of the difference image are then extracted using the split function in order to be able to add them together. It is important to note that the result of this sum may sometimes be greater than 255, but because saturation is always applied, the result will be stopped at 255. The consequence is that with this version, the max distance parameter must also be less than 256. This should be corrected if you consider this behavior unacceptable. The last step is to create a binary image by using CvThreshold function. This function is commonly used to compare all the pixels with a threshold value, the third parameter. And in the regular thresholding mode, CvThresBinary, it assigns the defined maximum value, the fourth parameter, to all the pixels greater than the specified threshold and 0 to the other pixels. Here, we use the inverse mode, CvThresBinaryInverse, in which the defined maximum value is assigned to the pixels that have a value lower than or equal to the threshold. Of interest are also the CvThreshold to 0 and CvThresh to 0 inverse modes, which leave the pixels greater than or lower than the threshold unchanged. Next, we will see the floodFill function. Our color detector class identifies the pixels in an image that have a color similar to a given target color. The decision to accept or not a pixel is simply made on a per-pixel basis. The CvFloodFill function proceeds in a very similar way with one important difference. In this case, the decision to accept a pixel also depends on the state of its neighbors. The idea is to identify connected area of a certain color. The user specifies a starting pixel location and tolerance parameters that determine color similarity. The seed pixel defines the color, that is seek, and from the seed location, the neighbors are considered in order to identify pixels of similar color. Then the neighbors of the accepted neighbors are also considered, and so on. This way, one area of constant color will be extracted from the image. For example, to detect blue sky area in our example image, you could proceed with this function. The seed pixel that is 100,50 is located in the sky. All connected pixels will be tested, and the ones having a similar color will be repainted in a new color specified by the third parameter. To determine if a color is similar or not, different thresholds are defined independently for values that are higher or lower than the reference color. Here, we use the fixed range mode, which implies that the tested pixels will all be compared to the seed pixel's color. The default mode is the one where each tested pixel is compared to the color of its neighbors. The results we will obtain will look like this. A single connected area is repainted by the algorithm. Here we painted the sky in white. Therefore, even if there are some pixels somewhere else with a similar color, in the water for instance, these ones would not be identified unless they were connected to the sky area. Next we will explore is Functor, or function object. Using the C++ operator overloading, it is possible to create a class for which its instances behave as functions. The idea is to overload the operator method so that a call to the processing method of a class looks exactly like a simple function call. The resulting class instance is called a function object, or a functor. Often, a functor includes a full constructor such that it can be used immediately after being created. For example, you can define the full constructor of your color detector class like this: color detector UChar, blue UChar, green UChar, red UChar, int max distance equals 100. Max distance. Here specify the target color and set target color as blue, green, and red. Obviously, you will still use the setters and getters that have been defined previously. The functor method can be defined like this: CVMat operator constant CVMat, an image, and then here color detection code. To detect a given color with this functor method, simply write this code, which you can see here. As you can see, the call to the color detection method now looks like a function call. The last one that we will be looking at is the OpenCV base class for algorithms. OpenCV offers many algorithms that perform various computer vision tasks. To facilitate their use, most of these algorithms have been made subclass of a generic base class called CV algorithm. This one implements some of the concepts dictated by the StrtegyDesignPattern. First, All these algorithms are created dynamically, using a specialized static method that makes sure that the algorithm is always created in a valid state, that is, with valid default values for the unspecified parameters. Let's consider, for example, one of these subclasses, CVORB. This one is an interest point operator. Here, we simply use it as an illustrative example of an algorithm. An instance of this algorithm is therefore created as follows. Once created, the algorithm can then be used. For example, the generic methods read and write can be used to load or store the state of the algorithm. The algorithms can have specialized methods. In the case of ORB, for example, the methods detect and compute can be used to trigger its main computational units. Algorithms also have specialized setter methods that allow specifying their internal parameters. Note that we could have declared the pointer as CVPTRCV algorithm, but in this case, we will not be able to use its specialized methods.